Hello.
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 Hello,
Good
sir.
afternoon to
Hello.
one and all. I am Basaraj Patil, Assistant Professor, Department of ECE, VTU, CPGS, Kalaburagi. Feeling delighted to introduce another eminent personality, Mr. Ravindra. He is presently pursuing his PhD in Biomedical Image Processing and Embedded Systems in JNTU, Anandpura. He has an academic experience of 9 years. He has been rectified as an assistant professor from JNTU, Anandpura. He is currently working as an assistant professor in Department of ENC Engineering in Chadalwada Ramanamma Engineering College, Tirupati, Andhra Pradesh. He, to add more about his achievements, he has published 17 international journals and he also has participated in 9 international conferences and 3 national conferences. He has participated in 17 workshops. Thank you. In sorry, I request all the participants, please turn off your mic, switch off your cameras. Thank you.
Ravindra sir, please proceed.
Start. Okay, sir. So, very good afternoon to everyone. So, this is Ravindra. So, working as an assistant professor in Department of ECE. So, I'm very glad to be here with the students of VTU. And I'm very interested to present some concepts regarding clustering methods in image processing. So, in actual, this particular concept, there is a clustering. It is a part of data mining. So, I think most of you students you have some idea about the data mining. So, it is just a process of mining some knowledge from the given data. Okay, so and then the clustering is one crucial process in that particular data mining. So, in the very first slide, I have just shown you one picture. So, in general, the clustering is nothing but a process of grouping. So, grouping is done based upon some object similarity characteristics. Okay, so you can observe in the very first slide itself, on the left side, there exists a bunch of vegetables. It is just a group of vegetables which seems to be randomly distributed. So, on the right side, there exists one more picture in which you can observe that the same like vegetables, they seems to group separately. So now this particular grouping is just called as clustering. Okay, so in this present lecture, we're going to deal with some basic concepts like these are the key contents that I'm going to discuss with you. So it is we're going to deal with what is a cluster analysis and the type of data that seems to be used in cluster analysis, and then the major categories, major classified clustering methods, and then I'm going to just give some examples of clustering methods like partition methods, hierarchical, density, and some other practical implementations. Okay, so these three, that is the partition methods, hierarchical and density based methods, these are mostly used clustering methods. Okay, so the very first thing is that what is the cluster analysis? Okay, so in actual, you have to know one thing, that a cluster is in general is a collection of objects. Okay, so collection in the sense we need to collect or group some data particles or data items that seems to be having some form of special similarities. Okay, that means we need to group the data points that seems to be having some common characteristics as one group, and then we need to separate them from the cluster which seems to having different characteristics. That's it. Okay, so coming to cluster analysis, so it is just uh, based upon finding the similarities between the data according to the characteristics found in the data and the grouping similar data objects. Okay, so it is of finding similarities between data according to certain characteristics. Now, for example, in the very first slide, I have just shown you the picture. So, in this particular picture, so the characteristic that I have considered to group them is the color. Okay, so on the left side, there exists so many colored vegetables that seems to be distributed independently. Now on the right side, you can observe that all these particles, they seems to be distributed separately. separately, and then this particular grouping is being done based upon one specific characteristic, that is its color, that is the vegetable colors. Okay, so that is it. Okay, so in the same way, I can give you one more example, that is in a class. For example, a class is a cluster. That is your general classroom is a cluster which comprises of elements like students. Okay, students are definitely boys, a group of boys, and then a group of girls. Okay, so the set of boys is called one cluster, and the set of girls is one more cluster. Okay, so now the clustering process is just based upon the gender characteristics here. Gender characteristics here. Okay, so here in the classroom, you can observe that the boys and girls, this is to be separated. This is to be made to see separately based upon their characteristic, that is nature characteristic, that is gender. Okay, so the applications this clustering involves so pattern recognition, spatial data analysis, and then image processing, economic sciences, and your World Wide Web. Okay, so pattern recognition in the sense, in general, a pattern in the sense, it is going to represent a schematic data that seems to having common characteristics. Now, for example, if at all we're going to have a shirt comprises of many patterns. Okay, so each and every pattern is just termed as a group of common colors. Okay, so this particular group is called as a cluster here. So pattern recognition in general, I can give you one more brief example. That is your thumb comprises of a pattern. Okay, so pattern every day while making use of your login, we are going to make use of your thumbprint as an access. Okay, so now here, what are the particular electronic gadget it is going to do? It is going to recognize the thumb pattern. Okay, so that is one typical example. And then a spatial data analysis. So this particular clustering process, it will be useful in some form of geographic information systems by clustering some space features. For example, it will be useful to cluster the data that is present in a satellite images. That means it will be useful to identify some form of common characteristics like a group of trees, for example, like forests, and it will be useful to identify the clusters of golds or minerals or some other things that seems to be present in the earth. And then it will be useful in image processing. Now, for example, if at all we are going to consider image processing, so image in particular, some form of brain hemorrhage images. You can observe that on the MRI images, you can see that there exists some tumors. So tumor is just termed as a cluster. Okay, so this particular cluster, it is going to have some group of affected, affected cells that seems to having some common characteristics. That means some form of bleeding, some form of protein accumulation, like that. So even this particular clustering process, it will be useful in economic sciences. That is, it will be useful in market research. You know, I can maybe observe one thing that whenever you go to some form of stores like Reliance and all, so in general, they used to get some form of feedback from the customers. Then they used to identify what is the type of products in which the maximum number of customers they seems to be buying. So that is one analysis. And even in the world wide web also. So there we can observe the data classification and cluster weblog to discover the group of similar access patterns. This is a typical example of your Google. Okay, so you can observe that last one, there is a cluster weblog data is to discover the group of similar access patterns. So what do you mean by this similar access patterns? For example, in the Google, you are going to search for one keyword. So based upon that particular keyword, the Google server, it is going to deliver so many web links, that seems to having similar patterns. So that is one typical application. So these are the things that I have already explained you. So examples of clustering, that is typical examples like marketing, land use, insurance, city planning, and effect studies. Okay, so marketing in essence, it will be useful to analyze the what is it? Buying characteristics of huge number of customers. And then land use, it will be useful to identify similar land use essentially present on the earth databases. And then insurances. So insurances, it will be useful to identify group of insurance policy holders with a high average claim cost. That means within the insurance itself, there exist so many fellows that seems to be making premium for very different amounts. That means it may be grouped in terms of some amount ranges like 10,000 or 10 to 20,000, 20 to 30,000, like that. Okay, so now this particular ranges, it is just termed as a cluster. And then city planning. Okay, so identifying grouping of houses according to their house types, values, and geographical identification. Okay, so now in a city, you can observe that there exists a bunch of urban areas and a bunch of rural areas. Those are also just termed as a cluster. Okay, earthquake studies observed earthquakes epicenter should be clustered along continental faults. Okay, so that is one more application. Okay, so the quality of good clustering is dependent upon the measures that seems to be useful to define to identify the hidden patterns. For example, if at all we are going to make use of one raw data input. Okay, so within that raw data input, what is the thing that we need to do is that we need to identify the cluster that we are most interested. The cluster that we are more interested. Okay, so in order to identify that particular cluster, we need to go for two things. That means grouping that particular items that are present within that particular cluster based upon two parameters. That is, they should possess high intra-class similarity and low inter-class similarity. Okay, so now what is this particular high and low intra and inter-class similarity? Okay, so high intra-class similarity in the sense these data element that seems to be present in a set, they must possess highest amount of similarity among them. And then they should possess a very less amount of similarity with the data point that seems to be present in the different cluster. That seems to be present in the different cluster. Okay, so these are the qualities. Okay, so you can measure the quality of clustering based upon the functions called the distance functions. Okay, so these distance functions, they will be useful to evaluate either the symmetry in between the data points or the dissimilarity in between the data points, which is just given in terms of d of ij. So where d refers the distance between the two data points, that is I and j and j. So now let us see some distance function that seems to be used in different types of data. Some type of data like intervalued, Boolean, categorical, some other things. Okay, so we'll concentrate on the very first two. Okay, so here there exists four different types of data. So one is interval scaled variables. So this is the common data that seems to be used in our traditional uses. And the binary comes under the digital systems. Some normal, ordinal, and ratio variables. These comes to business evaluations and variables of mixed types. So this also comes for business analysis, business marketing analysis. Okay, so now if you just observe this particular intervalued variables. Okay, so yeah, I have just presented you some two different metrics. So the very first metric is mean absolute deviation. Okay, so now if we just observe here, this is a distance metric that will be useful to identify the similarity or the dissimilarity of a data element with respect to a mean function value. Okay, so now here, this particular formula, you can observe that SF represents the mean absolute deviation, which is equal to the average of mean separation. Okay, so mean deviation from the data point. Okay, so here the x1, x2 up to xn, these are the data elements that seems to present in a set, and where MF is the average of that particular set, average value of that particular set here. So now our motto is to minimize this particular SF value. So SF value in the sense, so if at all there exists some form of similarity in between the x, that is the data points x, and then the mean value, then this particular difference will be closer to 0. So that is, if at all these two are similar, then this particular index value SF will be 0. If at all they are very dissimilar, then this particular SF value will be maximum. So now based upon this particular closeness, that is SF value closeness to 0, we can just group those X elements as a single group. So then there exists one more type of distance metric function, that is standardized measurement, that is Z-score measurement, which is just given by the ratio of the gap in between the data element versus the mean value divided by SF. So where SF is the mean absolute value. So in practice, we observe that this particular mean absolute deviation is more robust than using a standard deviation. So these are the other metrics. So one popular metric is mean Cauchy distance metric. That is, it is just simply equivalent to your Euclidean distance metric. That is some square root of the gap in between two different elements. Okay, so here it is the cube root of the distance between xi's versus xj's. Okay, so we can treat that this particular xi's as one set and xj's as one more set. Okay, so now if at all the difference, that is this particular dij value is 0, almost 0, then we can treat that the contents that are present in the set I and set j, they are similar. They are similar. That means we can form a group. We can form a group of I and j as together. So now if at all this particular dij value is not equal to 0, or it is having some maximum deviation, the plus value, some highest positive value, then these I and j, they are dissimilar. Okay, so therefore we can easily separate them. So a simple distance metric is Manhattan distance, where the q value is equal to 1. So in this particular dij value, if I put q is equal to 1, you will get this particular difference distance function. Okay, this is one more thing, that is binary variables. So just skip this thing. Next categories, different types of clustering methods. Okay, so here there exist three key clustering approaches. These are partition-based approaches, hierarchical and density-based approaches. Okay, so in the partition-based approaches, we are going to just segregate or group or produce some form of clusters by just minimizing the sum of square errors in between the respective data points versus centroid value. So centroid value. Okay, so I will just give you one typical example of this particular partition method. And then hierarchical. So here we are going to construct some form of dendrograms using that particular that means the dendrograms in essence are tree diagrams. So we can just make use of this particular tree diagrams to make some clusters, to form some clusters. And then finally, a density-based approaches. Okay, so density-based approaches, these are mostly used in the cases where there exists heavy amount of data in which it is very difficult to segregate each and every one. So this is far better when compared to the previous two methods. Okay, so let us see one typical example for each and every one, every approach. Okay, so this is a partition-based algorithm. So here you can observe that here we are going to construct a partition of a database D of n objects into a set of k clusters. Okay, so using sum of minimum square distance. Okay, so here now let us consider that there exists a data set D that is going to have n number of objects, n number of data elements. And then thing is that we need to group them as some k number of clusters, some k number of clusters here. Okay, so now for that what we need to do is that we need to generate an objective function. So this particular objective function is nothing but the minimum sum of squared distance that here it is concentrated. So here it is just given by dual summation of c minus t whole square, c minus t whole square. Okay, so where here c represents the centroid of that particular cluster and T represents the data element. T represents that particular data element here. So if at all this particular difference is less, then we can make a group. Okay, so simple typical partition based clustering methods includes k-means and k-means. Okay, so let us see a k-means clustering method. Okay, so here we just observe this particular typical example. Here on the left side, I have just shown you one picture where the data is seems to be distributed in a two-dimensional plane. Okay, so here we can observe that there exist two different clusters which seems to having different colors. Okay, so some light blue and thick blue, light blue and thick blue. Okay, so by just observing with our naked eyes, one can easily say that there exist two groups. Okay, so now thing is that it is this type of clustering can be done manually through machine. So a machine requires some form of algorithmic steps that is needed to group similar kind of data and ungroup from the dissimilar data. Okay, so now if you just observe in the side, so here there exists some pale blue points and thick blue points. So manually you can treat that this is one cluster and this is one more cluster here. Okay, so now for a machine using this particular k-means clustering approach, so here k represents the number of clusters. Okay, so for that mean represents the number of centroids that we need to use here. Okay, so now here now to make some group of two clusters, what we need to do that we need to initialize some two centroids. Okay, so here I have just placed some two red points. So these two red points, these are the data points that seems to present in the entire data set, which are highlighted as centroids, Okay, so now with this particular 2 points, what we need to do that we need to measure that particular minimum square distance. So here I have just shown you this particular minimum square distance, that is c minus t whole square. Okay, so here the c represents the red dot and ti represents the this pale blue or thick blue data points here. Okay, so now if at all this particular distance is shown to be minimum, somewhat minimum. Okay, so now what we need to do that we are supposed to form a group like this. Okay, like you can observe this particular ovals. Okay, so these circles, this is the set of initial grouping. Okay, so now again what we need to do that we need to update the cluster means. Okay, so now for this particular set there exists a center point. Okay, so this particular center point is nothing but the cluster centroid, that is ci value. So again you can observe that after regenerating this particular center value, you can observe that the center it has been shifted to these particular points, these two red points. They seems to be shifted from one point to other points. So again what we need to do, again we need to reassign, we need to recompute this particular difference, that is c minus t whole square. Okay, so based upon this particular difference, again we need to form one more group here. Okay, so now again here you can observe that again in the one more iteration the data it seems to move aside. So again the centroid seems to be varied. That means it has shifted its position. So what we need to do that again we need to compare the same distance metric and regroup like this. Okay, we need to reassign the group. Now this particular process it will be iteratively done until there exists no further way to group or separate these particular centroids here. This particular centroid. That means there exists a tight situation where this particular centroids will not be moved out. Okay, so at that particular point that we can treat that the clustering process is said to be done. Okay, so now one more type of clustering is hierarchical clustering. Okay, so the name itself specifies that it is just dependent upon the hierarchy of the data points that we need to cluster. Okay, so here there exist two ways to cluster this data. One is agglomerative and the divisive methods. Okay, so in the agglomerative process, what we need to do there? So let us consider that this is one data elements, that is A, B, C, D, and E. These are the data points that seems to be present in a set. Okay, so now let us consider that at the initial step, this A, B, C, D, and E, this seems to be treated as individual data points, individual data points. Now after that, what we need to do that we need to just measure the dissimilarity or similarity in between the respective data points, that is A versus B, A versus C, A versus D, and A versus E. Now if at all we are going to obtain a form of similarity in between any two data points, like here for example if A and B, they seems to be having some form of similarity. Now based upon this particular distance function, what we need to do that we need to just make a group of A and B, like this set, like this particular set. Now here you can observe at the bottom that D and A, there seems to having some form of similarity. So therefore we have formed a group. We have formed a group. Okay, so now with respect to D and E, the C is maybe having some form of closer resemblance. So further, again this particular C along with the set of D and E seems to be a group like C, D, and E. So finally, this particular AB group and then CDE group, they have to be formed. They are going to form a entire total data set. Okay, so now the divisive method, the process is reverse. That means we need to go from top to bottom. So in the agglomerative method, we have gone from bottom to top, and in the divisive method, we're moving from top to bottom here. So that means if you consider that this is the entire set, that is A, B, C, D, and E. This is an entire set. Now within this particular set, what we need to do that we need to produce some form of distance metering in between individual data elements. So now if at all there exists some form of similarities and dissimilarities, so we need to separate them as independent groups like AB and CDE. Now within this particular A and B, again what we need to do that we need to just compute this particular distance metric. So now if at all there exists some form of dissimilarities, then this A and B set, it seems to be separated like this, A and B. And then a CDE. So within the CDE also, if at all we are going to measure some form of similarity or dissimilarity metric, you can observe that the C seems to be different from D and E. So again, this particular C and D, E, they seems to be segregated. Okay, so they seems to form some different group. Okay, so just observe this particular picture. This is a typical example of this agglomerative nesting. So here I have just presented the three pictures in which you can observe that particular bottom to top grouping action, bottom to top grouping. So in the very first picture, you can observe that there exists independent data points that seems to be distributed randomly. So now you can observe that in the initial step, so the two or more number of data points that seems to be having some form of similarity, there seems to be made a group like this. And here also one more group. Okay, and then these 2 points, they are close to each other. So this will form one more group here. So now in the next step, what we need to do that we need to find out the data points that seems to be close to this already formed clusters. Now for this particular 2 points, this particular point, it seems to be close. So therefore, these 3 points will form a group now like this, And here also, these 2 points, they are as it is. And then here, if you just observe this, for this particular cluster, there exists one more point that seems to be formed one more group like this. So we can just club these 3 points as a single group. Okay, so these 2 points, they seems to be very far from these other points. So therefore, they will form one more different group. Now, if you just observe this particular picture, these particular 2 sets, they seems to be close to each other. So therefore, I can make one set of these 2 points like this. And then these 2 sets, they seems to be close to each other. So we can form a set of these 2 points here. So this is bottom to top grouping here. So in the divisive process, this particular approach is done in the reverse process. Okay, so this is going to represent the dendrogram action of this particular hierarchical method. So here you can observe that on the bottom there exists some blue points. So all these blue points, they are going to represent the respective data points. The data points, it seems to be grouped separately. So from bottom to top, you can observe that these 2 data points, they seems to form a group. And then if at all there exists any similarity with these 2 points with respect to this point, they will form one more group. So in the same way, the grouping of the remaining elements is also done like this. Okay, so finally, what we need to do that in order to form the different clusters, we need to just bisect this particular dendrogram by just making some form of slice at this particular point like this. So for this particular tree, if at all I'm going to just remove some branches like this. Okay, so branches cut just you will get the different clusters. Okay, so this is about hierarchical. So divisive. So in the divisive method, it has been introduced by Kaufman and Rosso in 1990. So where you can observe the reverse action of your Agnes technique. So in the very first stage, you can observe that there exists very big clusters, very big clusters. Okay, so now within these particular big clusters, what we need to do that we need to segregate these points by just making some form of similarity or dissimilarity functions. Now, if at all there exists some form of dissimilarity in between the respective data points, what we need to do? We need to just separate them as separate clusters like this. Okay, so again, within these particular subclusters, again, we need to employ that particular distance metric. So now if at all we are going to find out any form of dissimilarity, we need to segregate them into different clusters like this, different clusters. Okay, so now from a big cluster, we have attained small clusters. Okay, so this is the reverse action of your Agnes metric. So a final type of metric is this density-based spatial clustering methods. Okay, so the name itself specifies that it is a type of spatial clustering which is just dependent upon the density of data points. Okay, so now let us consider the procedure of this particular approach here. So now if you just observe this particular picture here, I have just represented so many data points. The seems to be distributed randomly here. So now thing is that we need to just form a cluster of these data points based upon certain constants. That means we need to form a circle of radius some 1 centimeter or 2 centimeters or so and so. And then we need to put a constraint that how many minimum number of points that must be accumulated within this particular cluster in order to treat it as a cluster. For example, within this particular example, I have just given one thing, that is we need to form a cluster epsilon of 1 centimeter in radius, and the minimum number of points that seems to be covered is 5. That means if at all I'm going to consider one data point as core, that is a center data point. From this particular center data point, I'm going to just draw a circle of radius 1 centimeter. Now this particular radius, if at all it is going to cover some minimum 5 number of points, then this particular circle, it will form a cluster. It will form a cluster here. So now if you just observe this particular center, from this particular center, there exists 1, 2, 3, and 4 and 5. So totally 5 along with the core, there exists 6 data points. That means the minimum required points is 5. So therefore, we can form a cluster of this thing. Now, if we just consider one more point, we need to just keep on move from one point to other point, and we need to draw a circle of 1 centimeter radius in order to form a cluster that seems to be having a minimum of 5 points. Now, for example, if you just observe some points like this here, this particular point, if I treat it as a core, if at all I'm going to draw a radius of 1 centimeter around this particular point. Now, if you just observe this particular circle, it doesn't possess the minimum of 5 data points. So therefore, it is not treated as a cluster. Okay, so it is just treated as a border point to the core cluster here. And in some cases, there is a certain data point that seems to be isolated. That means if at all we are going to concentrate those data points here, so we're just drawing this particular circle, that is a minimum 1 centimeter circle. You can't find no other data points except this particular point. Now this particular data point, it is just treated as an outlier. That means it is treated as a noise, which doesn't have any form of resemblance with the core data elements. Okay, that means it is just treated as an outsider. Just treated as an outside. So doesn't possess any meaningful information about this particular clustering process. Okay, so let us come to one practical application of mine. Okay, so I have been a research scholar in generative ML, and then I've been working on a typical application of diabetic retinopathy. Okay, so now this particular diabetic retinopathy, so it is a disease that seems to be present in the retina of eye, which is just triggered by diabetes. Just triggered by diabetes here. Okay, so in this patients, this particular pathology, it is just characterized by swollen and ruptured blood vessels and neovascularization. That means new blood vessels are being generated. Because now, if you just observe in some aged peoples, so aged people that seems to be having some prolonged history of diabetes, they seems to be complaining some form of visual losses. Okay, so now the visual loss is just due to an issue of swollen and ruptured blood vessels within the eye fundus, in the eye fundus, right? Now, what you have known one thing that in a diabetes state, in a diabetic condition, the body insulin levels, they seems to be distracted. They seems to be in an imbalanced state. In an imbalanced state. Okay, so now this particular insulin level, they seems to be uncontrollable. So with this particular effect, it is going to affect many crucial organs that seems to be present in our body. So the very first organ that is being affected by this particular imbalance of insulin is our blood vessels. Okay, so in actual, the blood vessels, they must be smooth and thin in order to produce certain minimum amount of pressure for the blood to flow in our body. Now, what happens if at all these particular blood vessels, they seems to be swollen, harden, and then get ruptured. So if at all they will get swollen, that means if at all there exists some form of inflammation, that means it is going to produce some form of BP fluctuations, blood pressure fluctuations. So that is also going to affect our body organs. Now what happens if at all these particular blood vessels, they will get hardened? If at all they will get hardened, the blood can't move from one point to other point. And in the same way, if at all the blood vessels, they will get ruptured, what happens? The blood will definitely leak into our body parts, into our body parts here. So now these particular blood particles, they will be accumulated in our body parts as some form of clots. Okay, so now these particular clots, if at all they seems to be accumulated in our eye, they are just as exudates. Okay, so these are the exuded particles of blood, and then protein and fat particles along with the blood. Okay, so if at all these particles, they will get deposited in our eye, they will definitely obstruct our vision flow. So therefore, these clotted particles, they will form some form of shadows on our eye. Okay, so this particular diabetic retinopathy, it is just classified into two types. One is non-proliferative diabetic retinopathy and proliferative diabetic retinopathy. Okay, so in a non-proliferative diabetic, it is just an acute state of diabetic retinopathy. So where you can observe only swollen and bulged, hardened blood vessels. But in a proliferative diabetic retinopathy, the blood vessels, they seems to get ruptured, and then there seems to be leaking some form of blood into our interior eye. So this is a typical example of your normal eye versus eye with the condition called diabetic retinopathy. So here you can observe on the left side picture A, it is going to represent so many key parts of our eye. So this is the fundus eye. So this is the interior part of our eye. So where you can observe the central part, that is macula, and then here you can observe some form of blood vessels, arteries and veins, ventricles. Okay, so then here there exists a central retinal part, and then central veins, and then optical disc. So optical disc, it is a nerve connection in between our eye and then our brain here. So in certain cases, even this particular optic disc also get damage. So what is I think you know about optic disc. Optic disc, it is just a nerve that will be useful to convert the light signal into electrical pulses and then transmit these particular electrical pulses towards our brain. Okay, so now in our diabetic retinopathy condition, these blood vessels, they will be get ruptured, they will be bulged or get ruptured. Okay, so if at all these blood vessels, they will get ruptured, they will leak out some blood and fat and protein based particles. These fat and protein based particles, they are just accumulated as exudates. So these are termed as hard or hard exudates or soft exudates, where soft exudates are termed as cotton wool spots here. Okay, so that's it. Okay, so now if you just observe here, So this is a typical example of the vision in a normal fellow versus vision in a patient where he's been suffering with diabetic retinopathy here. So in a normal vision, it doesn't seems to be having any distractions. Okay, it is quite clear and smooth. But in a patient with the diabetic retinopathy condition, you can observe that there exists some black spots. So black spots in the sense these are the shadows of these exudate particles here. Okay, so and then the vision it seems to be very blurred here. Okay, so our my motto is to identify these particular particles using some form of clustering methods. Okay, so this is a typical fundoscope image. I think most of you have observed this particular kind of image in your clinicals, ophthalmology shops. Okay, so this is an device called as digital fundoscope that is useful to capture these particular images. Okay, so I'll go to this particular thing. So my problem is being motivated with some form of clinical issues like dilation of pupil. So I think everyone has gone through some form of eye checkups. Okay, so during eye checkups, they used to put some form of drops, like mitotic drops, so which is going to produce some form of side effects like burning sensation, eye irritation, sensitivity, blurred vision. Okay, so these kind of side effects they will last for hours to days. This is one problem, and then moreover, the ophthalmologists, that means the count of ophthalmologists over the globe, it is very less when compared to the diabetic patients here. So there is one more motivation. Okay, so now if we just observe this particular table, you can observe the global scenario of the number of countries that seems to be having this particular ratio, that is ophthalmologist count versus million inhabitants. So million inhabitants in the sense the number of persons present in the particular country. Okay, so now out of this number of countries, only 18 countries they are going to have more than 100 number of ophthalmologists per million inhabitants. And then 74 they seem to be having less than 100, and some 48 they seem to be having less than 25. Some countries, some underdeveloped countries, they seem to be having even less, that is less than 4, and even very, very less here. So this is one more flaring gap in between the number of diabetic patients versus ophthalmologists. So this is going to create some form of issue like diabetes diagnosis and screen. Okay, so this is a literature that I have gone through many journals. I just verified some issues here. So these are the things that I have found, that I observed that there exists no state of method that have utilized spatial characteristics of the pixels in an image for lesion detection. Okay, so they didn't bother about the neighborhood of the lesion pixels that will be useful to carry some key characteristics of a lesion cluster. Lesion in the sense it is the exudate particle. Okay, so then there exists lesion detection methods which seems to use a multiple number of stages. I found that there is so many authors. They have used a multiple number of pre and post processing stages. Okay, so these are pre and post processing stages. They are going to cope up lot of lag in the simulation process. So that is one disadvantage. That is one problem that I observed. And then I observed one more thing, that no method has used kernel-based methods. Kernel-based methods. Okay, so let us see what are kernel-based methods here. So this is a data set that I use. And then I just employed this particular work on two different platforms. One is a personal computer, and then a Raspberry Pi 3 model big kit. So this is a typical example that I have simulated my problem on a Raspberry kit. You can observe that the input and the respective output image, where you can observe the yellow particles that seems to be highlighted. So this is the hardware specification. So fuzzy sequence clustering. Okay, so you have known about the particular fuzzy sequence clustering. Okay, so in which the clustering is being done in an unsupervised fashion. So in which the clustering process, it is being dependent upon the membership function here. So on the previous slides, we have observed one thing, that is a distance metric. So here, this particular JFCM, it is going to represent the objective function that we need to minimize in order to find out some form of similarity in between the data points xi versus the cj. Okay, so here we need to, for a data, for example, if at all x represents the pixel that needs to present in our input data, and then from this particular data, we need to randomly select some cj number of clusters, cj number of cluster centroids. Okay, so now, and then we need to measure this particular difference, that is xi minus cj gap. So now if at all there exists very less gap in between these 2 points, then these 2 points, this seems to be form a cluster. Okay, so now this particular process, it will be keep on iteratively done until you can't able to move this particular cluster centroids here. Okay, so now in this particular JFC, I observe one problem, that is it is going to make use of an Euclidean distance metric. Okay, so using an Euclidean distance metric, we can able to detect only the lesion cluster that seems to having spherical shape only. But in practice, there exists so many clusters that seems to have varied amount of shapes. So for this particular thing, this particular JFC, it is going to result some unwanted results. Okay, that means we are going to lose some more key region of interest. Okay, that is the problem. So these are the merits and demerits that seems to be found in the FCM method. So they are very simple and effective and easy to design, very flexible to operate on data points, and they can obtain very best results for overlap data. But you can observe that they are very less immune to noises, and then they are going to make use of Euclidean distance metric, which will allow the detection of only spherical shaped objects. That is it. And then they are very less feasible while dealing with non-linearly separable data clusters here. So let us see what is the non-linearly separable cluster. Now, if we just observe here there exists two pictures which is going to represent two different types of clusters. On the left side, there exists these data points, which is blue clusters and then some form of red clusters. It seems to be easily separated using a single line. Okay, so now this particular set or this particular data, it is just termed as a linearly separable data. Now on the other side, just observe here, these particles, they seems to be randomly distributed. Now in order to separate these 2 points, what we need to do is that we need to draw a non-linear line. That is some form of line that doesn't possess any linear characteristics. Okay, so now dealing with this particular type of non-linear data, it is very hard for this particular FCM method. Okay, so now in order to deal this particular non-linear data, so what I did is that I just employed, just transformed this particular non-linear data onto a kernel space. If you just observe this particular picture, yeah, this is the input two-dimensional space where you can observe so many data points. Now, these data points, they seem to be separated using a non-linear line, non-linear decision function. We just call it as non-linear decision function. So using this particular two-dimensional space, it is very difficult to separate these two clusters. Okay, now thing is that if at all I go to map these particular data points onto a three-dimensional space like this, that is the three-dimensional space is termed as kernel space, where you can observe that the blue particle, they seems to move up, and then the red data point, they seems to move down. Now in between, I can just make a separator which will be useful to separate these two clusters. Now this particular separation is a simple linear plane. So that is it. That is one flexibility of using a kernel space here. Okay, so now I just employed one more thing, that is I just consider the local characteristics of a filter. That is, I just perform some form of convolution matrix on a neighborhood like this. So I just consider a set of 3 by 3 data points that seems to present in an image. On this particular data point, I have just applied a 3 by 3 filter like this. So I just employed some form of convolution here. So then this particular E processor value, it is a resultant processor value that seems to map in the final image. Now, what is the significance of this particular method is that we can give some form of weightage to the central element. So one such field kernel that I use is a Gaussian kernel. So this is a two-dimensional kernel that is going to give much importance to the center element. Center element. That means it is going to give maximum weight to the center element. So I just propose some 4 different types of methods. One is multi-kernel induced spatially weighted fuzzy Siemens clustering method, and then spatially weighted possibilistic Siemens clustering algorithm, and then multi-kernel induced possibilistic Siemens, and then multi-kernel induced spatially weighted Siemens PCM method. Okay, so let us see one more thing. This is the proposed diagram. So you can observe that I have just implemented this particular clustering approach using very nominal pre-processing stage, that is just made use of a green component as an input to the proposed algorithm. Okay. Now in the multi-kernel induced spatially weighted fuzzy clustering method, so what I did is that I just employed this particular FCM clustering process by just mapping the data points onto a cluster space. A cluster space. Now within the cluster, I can easily segregate them into two different or two or more number of clusters using a common single linear plane. Give me plane here, and then this particular data, it is being spatially weighted. So these particular spatial weights, they will be useful to make the system more immune to noises. Okay, so this is the objective function. So this is a kernel metric. You can observe the kernel metric. It is a nonlinear function that will be useful to map the two-dimensional input data into a kernel space. Okay, now within the kernel space, we're going to apply that particular difference. Okay, so then here H represents the spatial function, that is the Gaussian spatial function that I have represented, and then Mij represents the fuzzy membership function. Okay, so here the fuzzy membership function is going to represent the degree of belongingness of a particular data point towards a particular centroid. Okay, so that is one thing. So our motto is to minimize this particular objective function, that is J mk sub cm here. So this is a pre-processing. The pre-processing, I just taken one typical example of image. So I think most of you know that a typical image comprises of 3 components, that is on red, green, and blue component. Red, green, and blue component. Okay, so these 3 points, that is B, C, and D, these are the red, green, and blue components. You can observe that the red component seems to be having more brightness. Green, it seems to have more contrast value. So that means we can easily identify the gap in between the foreground versus the background. While the blue component doesn't carry any bright information, just carries only dark information. This particular green component I have just taken as an input. Now this particular green component may be having some form of inherent noises. One simple technique to avoid any form of noises is median filtering. That means we are going to make use of neighborhood. Within the neighborhood, we are going to take out the median value as a processor value, and then it is mapped onto the output image. Now in the output image, that is in the median filtered image, you can observe that the image seems to be slightly enhanced, and then the edges of this particular data point, it seems to be preserved. So that is one typical feature of this particular median filtering. So these are the different images that is been taken from different databases. Okay, so then these are the end results. So I have employed 2 different kernel metrics. One is single Laplacian kernel and then dual Laplacian kernel. So within this particular thing, so within this particular images, you can observe that these are the retinal images on which you can observe that there is some yellow and white patches. So these are the sedimented particles that seems to be accumulated within our retina. So our motto is to segregate these points. So like this. So our clustering process, we have attained all those soft and hard exudate particles separately. So you can observe that picture E, you can observe that there exists minus specks. Even that thinnest specks are also highlighted in this particular method here. This is one more thing, that is we have employed dual kernels, dual Laplacian kernel induced spatially weighted fuzzy Siemens method. Okay, so these are the spatial metrics that I have employed: sensitivity, specificity, and accuracy. So the sensitivity, it will be useful to determine the trueness of this particular method to identify the target lesions. And the specificity represent the reverse. I mean that it is going to represent the ability of the system to identify the non-lesion signal. And then accuracy, it is the amount of segmentation accuracy here. So these are the values that I have achieved using this particular L1 KS FCM and L2 KS FCM. That is, I have achieved around 80 plus percentage of each and every parameter here. So these are the graphical representation of each and every image. I have used around 40 images as the test examples, and then these are the variation of this particular sensitivity values versus normalized sensitivity ranges. Okay, so you can observe that all these particular points, they are going to represent a convergence point of 0.8 to 1. That means the minimum requirement of convergence is around 80%. So almost for all the images, this particular method it has attained maximum above 0.8 value. But you can observe that there exists some images where you have attained a very less sensitive. That means closer to 0.7. So this is because I have used some very less resolution images, less resolution images, which doesn't produce a good sensitivity value. So that is it. So I meant to verify this particular method for both the high resolution and also low resolution images here. Okay, so in the same way, there is a normalized specificity. It seems to be almost closing to 1. And then this is the accuracy. So it is more than 80% I have attained. And then one more thing is that spatially weighted PCM. So PCM, in the sense, it is a possibilistic Siemens clustering method. It has been developed by Krishnapala and Keller. So one particular problem in the FCM method is that there exists a rigidity to force the data elements of a membership value that is present in the FCM and its derivative. It means in the FCM method, there exists one particular problem. That means at the initial stage, the user has to give some forced values of membership function to each and every pixel which seems to present in a data. So that is actually a great flaw that seems to be present in the FCM. So now in the PCM, what they did is that they have removed this particular rigidity by just making some one more constant, that is possibilistic constant here. So this is termed as eta I. So it is an objective function that is used to determine the inter-cluster similarity here. So in order to minimize this particular function, we need to just differentiate this particular JSFCM with respect to Mij and eta I. Okay, so that is it. So if at all we are going to go to at a minimum J value, then we can treat that those two particular data points are treated as a one cluster. So the images I have taken, these are the end results. So here also I have obtained more than 80% of each and every respective parameters. So this is the graphical analysis. You can observe that all these plots, this is to be converging in between 0.8 to 1. This is the minimum requirement. And one more thing is that application of this particular PCM in a kernel domain. Okay, so I have explained you about the kernel domain. So this is the objective function of kernel induced PCM. So where you can observe that there exists a K function. So here the K is a nonlinear function that will be useful to map the two-dimensional data pattern into a three-dimensional space, data space, where you can easily segregate the data points into two different or multiple number of clusters using a linear plane here. So, and this is one more thing, that is a spatially weighted KPCM. So spatially weighted kernel induced PCM method. Okay, so here I've just modified this particular Mij. This particular membership function is being appended with a spatial weight. Okay, so this is a weighted metric of the previous KPCM method here. So this is the end result that I have achieved. You can observe that this particular two methods, that is single Laplacian kernel and dual Laplacian kernel of both these methods, they have attained finest details of these particular regions. And then this is the statistical parameters that I have achieved. So here you can observe that this particular method, it seems to be produced almost let's see values here. So everything, it seems to be converging in between 0.8 to 1 here. So this is a statistical evaluation of my proposed methods with the existing methods. I have taken around some 30 plus papers, seems to be published in the last 2 decades. So this is the graphical view of my proposed method versus the existing methods. So here you can observe that compared to the existing methods, my methods essentially attain almost good statistical values. That is a maximum of 93.15% of sensitivity. And then here, this is a graph of specificity. So here also I achieved around 99% of specificity and compared to the remaining methods. This is the accuracy plot. It also around 90 plus accuracy. So this is one more graph which is going to represent the amount of time taken for total number of iterations. Okay, so I have just taken one example image, and that example image I have iterated for some maximum of 100 iterations. Now each and every method seems to be attaining some convergence for this number of iterations, 82 number of iterations, 82, 79, 91, so on. So now the time taken for this number of iterations is around 129 seconds, 138, so on. So now the ratio of Ni by It will give certain parameter, which must be very less. Now we just observe this particular ratio Ni by It. Here, this particular method SPCM, it has achieved a very less ratio. So that means this is very good for dealing with high dimension data. Okay, so that means we need to simulate any form of data clustering within less amount of time. So for to attain a very high speed clustering process, this particular ratio, that is Ni by It, is Laplacian and dual Laplacian method. This ratio of around 0.87 and 0.80. It seems to be very high when compared to the remaining methods. So using a simply kernel induced methods, this particular ratio seems to be drastically improved. Now, if you just observe the last 2 methods, these are spatially weighted kernel metrics. Okay, so now this particular ratio, if you just observe this Ni by It ratio, it is again reduced. So now I just observed one thing, that the inclusion of spatial metrics into any form of clustering methods, they are going to reduce this particular ratio value Ni by It. Okay, so which is most predominantly required here. Next, this is the graphical view of the Ni versus It for the proposed methods. So here you can observe that the SPCM method seems to be having less number of iterations, but they seems to be taking more number of time. Now, if you just observe the last 2 methods, they seem to be having somewhat a bit lesser simulation time and compared to the remaining methods. So finally, I just want to conclude that, so just make use of simple clustering methods, it is very difficult to deal with some form of nonlinear data. So for that, it is good to employ, or very good to transform the 2-dimensional data onto a high-dimensional kernel space, and then appending some form of spatial weights onto them, we can easily segregate them and will make the system more immune to noises. Okay, so finally, I just want to conclude my lecture. Dr. N. Pravinkant Reddy, so he's a senior ophthalmologist working in Sutrama Eye Hospital, Madanapalli. So he has helped me in many ways to attain certain form of conclusions, and he has provided many images taken from some reputed hospitals, and which I just used them for my simulation process. So these are my recent publications. There exists one paper that is included in wireless personal communication as finger publication. It is indexed in SCA, Science Citation Index. So thank you. So these are references. Many thanks, sir. No, thank you, sir. Thank you, sir.